Hi there, my name is Christopher Worse and welcome to homework 3 for Transport 1. This video is going over part 1, which asks us to write, explain, and test code to calculate the friction factor, the head drop given flow, and flow given head drop for a pipe segment. Now if you notice there's an optional bit down there that asks us to do all of that for a actual pipe network. But for at least this video, we're not going to touch that. We're just going to do part 1. So as you can see up on the top, I have a pull-up for reference of the Churchill equation that we'll be using later, as well as our code, or at least a spot to write our code, again, after I do the usual and write the derivations out on the screen, out on the whiteboard behind me. So per usual, we're going to start by drawing a picture, and so we're going to be using either, there are two ways that we can set this up. We can set this up such that there is a pressure difference given by a pump, so that at point 1 and point 2 there is a pressure difference, P1 and P2. That's one way to do it. Or we could do it such that there is a tank full of liquid that drains downwards, and that the motive force, the reason for the pressure differences, is in fact the change in height of the pipe. Either way, it really doesn't change anything. And we're going to start by, again, as we do all the homeworks, writing out the equations that we're going to be using. So we're going to need Bernoulli's equation and volumetric flow rate. So we'll start with Bernoulli's equation. So the pressure difference between states 1 and state 2 divided by the density plus the velocity difference squared between states 1 and 2 divided by 2 plus the gravitational constant g multiplied by the height difference between the two positions z2 minus z1 is equal to, as we know, the negative of the frictional heating. We also have our Q, our volumetric flow rate, is equal to velocity times area, which means that Q is equal to velocity times, if we're using diameter, it'll be pi times diameter squared over 4. You'll see why we need the diameter in just a second. So, as we've talked about in the actually the previous homework 2, we found what the, or we know what the frictional heating is. Frictional heating is actually 4 times the fanning friction factor times the change in position divided by the diameter multiplied by the velocity over 2. So I'm just going to plug that in up here. Is equal to negative 4 times the friction factor times the change in position divided by the diameter times velocity over 2. I can erase this. And now, because we're looking at a specific pipe, we're going to assume that the pipe is not changing diameter. It is not getting thinner, it does not taper, it does not get wider. Therefore, the velocity of the liquid flowing through it is constant. So we can just get rid of this right here. Now, we also know, based off of what we have pulled up here, I'm actually going to pull it up right now. We are going to be using the Churchill equation to find this friction factor. So I will write that out. Churchill. So the friction factor, F, is equal to 8 times 8 over the Reynolds number, which, by the way, Reynolds number, RE, equals density times velocity times diameter divided by the viscosity of whatever liquid we're talking about. Okay, 8 divided by the Reynolds number, 1 to the power of 12, plus 1 over A plus B to the power of 1.5, all of that to the power of negative 12. Or actually, no, 1 over 12. Now, A plus B are their own expressions, so they have just underneath. So A is equal to 2.457 times the natural log of 7 divided by the Reynolds number, multiplied to the power of 0.9, plus 0.27 epsilon over d. This epsilon is the roughness of the pipe, and the diameter, d is just diameter. We are actually going to represent this specific epsilon over d, the roughness divided by the diameter, as its own variable in our code, but then we'll get to that later. All of that is to the power of negative 1. And then all of this is to the 16th power. Now, if you know a natural log, you know that a natural log to the power of negative 1 is just a negative out front. So we get rid of that negative 1 just to make coding and the expression itself a little bit easier. And then B is short, it's nice and easy, unlike its cousin A. 37,530 divided by the Reynolds number to the 16th power. A simple little expression that gets real big. All right. So now that I have that copied out, I'm going to go back here, and we want the friction factor. We have that here. So trivial. Friction factor is done. Now we want the head drop given flow, and then the flow given head drop. So we need to change this. What he's asking for head drop. We want the head Bernoulli's equation. It is an engineering or a massaged Bernoulli's equation that gives an easier time for solving problems. So that's going to basically all we're going to do is divide g, the gravitational constant, across. That's it. So head drop, we'll call it HD, is the pressure difference between states 1 and 2 divided by gravitational constant and the density plus the difference in height between states 1 and states 2 equals negative, these cancel out, so 2 divided by gravitational constant times the friction factor times the change of position divided by the diameter multiplied by the velocity. So we have this, and really the head drop is just here. This is all we need for the head drop. All this bit here. Because if we have this, we can code out a head drop an equation, and then give it a guess for a head drop, and later use root solver to really change our flow until we get to that true head drop. Either way. That's later. But all that really matters is that HD is equal to it's actually equal to the positive 2 divided by G, which means a negative head drop here. The gravitational constant, 2 divided by the gravitational constant multiplied by the friction factor multiplied by the velocity multiplied by the change of position, divided by the diameter. which of course means that the head drop minus this expression here equals 0, and we'll be using this later in, as I mentioned, in our final root solving to find the head drop. Now, we have Q up here, we have velocity here. This, what is this? I think this is v squared. Yes, this is v squared specifically. So we're now going to take this and move everything over and solve for v. We're going to solve for the velocity so that we can get to q here. So we know that, or by moving everything over, v, the velocity, is equal to the square root of the head drop multiplied by the gravitational constant g multiplied by the diameter of the pipe divided by 2 divided by the friction factor divided by the change of position. That will just be the length, but that's not very important here. And we also know that Q is equal to V multiplied by pi times the diameter squared over 4. So now that we have all of that, what we're going to be doing is taking this Churchill to find the bending friction factor. That's going to be the easy part. We're then going to be using this head drop equation and this flow equation and using a root solver and functions to find both of these at once. So with that, all of the derivations are finished, and we're going to transition over to the coding. All right, so now that we have our Python open and we're ready to code, and we've already derived all of those equations that we're going to be using. I'm going to start by importing the necessary softwares and necessary tools. So we're going to import NumPy, numerical Python as NP. We're going to import the root solver from SciPy Scientific Python Optimize. Import root. Good. We are and we're going to start. That's all we need to run this, or at least the bit that we're doing right now. So all we're going to do is we're going to start with the Churchill equation. So we're going to define a function. We're going to name it Churchill. And all that we need, I have the sheet right here with some of the equations written down on it. We need the Reynolds number, and we need that epsilon over d constant, the pipe roughness divided by the diameter constant. So Reynolds and ED. Name that there. So we know that F is equal to 8 multiplied by 8 times 8 divided by the Reynolds number to the power of 12 plus 1 divided by A plus B to the power of 1.5, and all of that is to the power of 1/12. Oops. There. We also have the expression for A. A is equal to 2.457 times numpy log. Numpy log is just the natural log. Log 10 would be a base log. The log of 7 divided by the Reynolds number to the power of 0.9 plus 0.27 times ED. And right, this is negative. All to the power of all to the 16th power. And then we have B. B is equal to 37,530, I believe. Let me double check that. Pull up that equation. Yes, 37,530 divided by the Reynolds number to the 16th power. Good. Then we can return F. Actually, we don't need to define F there. We can just return this value instead. And good. So now we have an equation, our Churchill equation, to find the friction factor. Next, we want to define a head drop, our head drop equation. And for that, we're going to need the length of the pipe, the velocity, the diameter of the pipe, and the friction factor. So let's do F. Friction factor. Going to need a given Q, our given flow. Q, L, a length, which we're just going to be using for delta X, the change of position. The diameter of the pipe, and we want our roughness as well because we're going to be using the Churchill equation. So, ED. And there, and for this actually, I'm going to want to enter some constants so that we can actually find the Reynolds number instead of giving the Reynolds number. So, let's do mu, the viscosity of colored water is 1e negative 3. This is Pascal seconds. The density of water is 1e3, 1 to the power of 3, or 1,000 kilograms per meter, per cubic meter. And then we want G, and our gravitational constant is just 9.81. All right, so we have that. We want to define the head drop. So we need to find the Reynolds number. RE is... Do we need to find the Reynolds number? No. We just need to find... Yes. So remember the head drop is equal to 2 divided by the gravitational constant multiplied by the friction factor, multiplied by the length divided by the diameter, multiplied by the velocity squared, divided by 2. So we're going to first start off by finding the velocity, and we have our own equation for that. Remember that the volumetric flow rate is equal to velocity times the area, and we found earlier that the velocity is equal to 4 times, we're going to be using an absolute value of Q divided by numpy pi multiplied by the diameter squared. Good. We also want to find the Reynolds number, and the Reynolds number is just mu Vd over, or rho Vd over mu. The density multiplied by the velocity multiplied by the diameter divided by the viscosity. So rho times v, velocity times the diameter, divided by mu, the viscosity. And then for the friction factor, we are going to use our Churchill function. So Churchill, given we know the RE and our pipe roughness ratio ED. Notice that ED, that ratio is given in both the head drop and the Churchill functions. So the value given in the head drop is the value that we used in the Churchill equation. And with all of that done, we can return the value for the head drop. The head drop is equal to 2 times F times the friction factor times the length times V squared divided by gravitational constant times diameter. Good. Shift enter. Let's do a quick double check here. Call it 0.1, 1, 0.1, and 1e negative 3. Actually 1e negative 6, and let's make this kind of longer pipe, a little bit smoother pipe. That way, whoops, I forgot to actually give values. So it gives us a value for the head drop, and this head drop here is what we're going to be comparing to a given value of a head drop. We're just going to name that HD in our flow function that we're going to be doing next, to then compare the two to find the flow. So we're going to define flow given a head drop HD, given a length, given a diameter, given a roughness diameter ratio. So for this, we're going to want to find the velocity, again, but a different velocity this time. Remember, we found that velocity is equal to the numpy is equal to the square root of, and we want this numpy dot absolute value of the head drop, and I will explain why we're doing this absolute value in a second, multiplied by the gravitational constant multiplied by the diameter divided by 2 multiplied by the fanning friction factor times the length here. And then we're actually going to be giving a guess of this fanning friction factor. It doesn't really matter too much what it actually is, because the head drop is going to be changing things. The root function at the end will use it and then solve it at the end. Let's actually make this 0.01 there. We also want, and then we're going to call this Q guess, a guess for our flow rate, because we're actually going to find the flow rate at the end, the true flow rate, and return it out. So our Q guess is equal to, we know that it's equal to this pi multiplied by the diameter squared multiplied by the velocity v divided by 4. Now, what happens if this head drop is negative? That gives us we already put in our absolute value for this, the head drop, so that we have don't have a negative under a square root, because that will return an error. However, if the head drop is negative, that also means that the flow must be negative. So we're going to need to put in something else to copy the sign of our head drop onto our flow. So I'm going to be using numpy.copySign. We're just going to take this, and given our head drop value here. So what this will do is it will take this equation and then give it the sign. It will take the value of this equation, and then give it the sign of the head drop, so that QGuess always has the sign of this head drop given here. So if head drop is negative, HD is negative, then our flow guess is negative as well. That doesn't matter in part one, because we should not be getting negative head drops. However, if we go further and we were to make a network flow code in order to find the flow through all of the pipes in that diagram below, then this absolutely would matter. But either way, we have this here, and now we want to write out our equation for the root solver to find. So we're going to define another function. We're just going to name it EQ for equation. But this one we need to give a vector of values, because root only accepts vectors into its code. This will only be a one value vector. It'll be q. Q is equal to yeah, 0. And then we're just going to return a head drop, or is this HD instead? Yeah. Actually, no, this is Q. Yes. Because we're going to be changing our Q here so that return, we want head drop HD minus our head drop equation, given Q, our length, our diameter, and our roughness. Oops, let me check here. Good. So now that we have that, we can return a root function. Return root root function, so EQ, our equation. X naught, we want to use our Q, or our Q guess, and that should be it. So if we shift enter, there's no immediate errors, which is good. And then if we find flow, given our value here for our head drop here, so given 36.96 as our head drop, and we're just going to copy over the same values, 1e -6. Now, what this should do is give us a value very, very close to 0.1. That would mean that our head drop and our flow equations are working together to get the same results, basically. So if we hit shift enter, it gives us an array of values. So, which means I need to .x 0, because it's giving us an array there, 0.099996, or very, very close to 0.1, which means that all of this has worked together to give us our true flow through the or if we were to give any specific head drop or values through this, it would give us the true flow through the pipe. Which means that we've finished homework 3, and if we wanted to, we could take this even further to do a whole network of pipes. But with that being said, thank you very much for watching. I hope you have a wonderful day.